This lecture is on heap sort, and their time complexity analysis. Here's a roadmap of what we will cover. In this video, we will cover the highlighted topic on heap sort, including how to build a heap and how to apply a heap to sorting tasks. Of course, we will also cover their corresponding time complexity. For simplicity, we will stick to covering only max heaps instead of switching between max and min heaps. Let's get started. To be able to use a heap for sorting purposes, you will need to build a heap first. However, the data that you may need to process is highly likely to be in a linear structure, like an array. How do we build a heap given a linear data structure like an array? There are two possible strategies to get this done. We will go over them one after another. Let's do the more naive strategy first. Under this naive strategy, you will start by preparing an empty max heap, or say an empty array of the same size as the given one, but you will treat this array as the data storage for your max heap. After that, you can iterate through the elements of the given array and keep calling the max heap insert method to insert each of those elements into this new heap. By saying the insert method of the max heap, I'm referring to one of the basic operations of heaps. In case you don't know it, you can watch it here in one of the prior lectures. What's the worst case time complexity for this naive strategy? The first insertion will take a constant amount of time, because the heap so far contains no other elements yet. The second element will run on big O of log 1, where 1 is the size of the heap. Remember, the time complexity of the insert method runs on big O of log n in the worst case scenario, where n represents the size of the heap. The third element runs on big O of log 2, where 2 is the current size of the heap. This goes on, and the last element will run on big O of n minus 1. Okay, now you know the time complexity of each insert method being called to build the heap. All it remains is to add them up. Roughly like this. So what does this lead to? Based on the logarithmic product rule, you can combine all these different terms just like this. The ending result will be log of n factorial. We know that the factorial of n is certainly smaller than n power to n. Yet log n power to n can be converted to n multiplied by log n based on the logarithmic property. As a result, we have an upper cap that's more familiar to us, which is n log n. That's the naive strategy and its worst case time complexity analysis. It's worth saying that although this strategy is straightforward, it's rarely used in building heaps from arrays because it's not very efficient. That is why we need to talk about the second strategy. Under this strategy, we won't prepare a new heap at all. Instead, we will treat the given array as a heap whose property needs to be restored. After that, we will traverse from the last non-leaf node to the root node. During this traversal, we will keep applying the heapify method to each of the nodes. So what heapify method? The same method that we covered when we discussed the delete method. The steps of the heapify method are presented here on the screen. The purpose of the heapify method is to restore the heap property of a subheap given its root index. Well, of course, here you have an assumption. The assumption is that the root node is a culprit, or say the root node is the one node that breaks the heap property. The heapify process achieves its purpose by iteratively swapping the root node value with its largest child until it reaches a proper level. Translating the step to pseudocode, you will have the same pseudocode that we covered in the past, like this. The heapify method takes a single parameter, I, that represents the index of the root node of a subheap, and it relies on the help from a helper method named maxChild to identify the largest child of a parent. Despite of knowing the heapify process and all the steps of the second strategy, there might still be a key barrier for you to get started implementing it, which is the index of the last non-leaf node. So the index of the last non-leaf node is always n divided by 2 minus 1, where n is the heap size, or say the length of the given array that is used to store the heap data. For example, if you use the array on the left side as an example, its size is 6. Its last non-leaf node is 6, whose index is 2. We can use the array size 6 to divide 2, then subtract by 1. After that, you will get index 2, which is the index of the last non-leaf node. You can use induction to prove this if you want. Here, we will just take some leap of faith and use it as it is. Based on the given steps in this strategy, the pseudocode is extremely simple. You only have a for loop that traverses from n divided by 2 minus 1 to 0. Inside this for loop, you will keep calling heapify on each of the nodes you visit. Let's try to apply this process to an example so that you can get a better sense of how it goes. We will simply use the example on our left side. The last non-leaf node is 6. When we apply heapify on it, we are actually trying to restore the heap property of a subheap, which only contains 2 nodes, 6 and 4, like this. Yet this is already a max heap, so we don't need to do anything. The for loop will take us to the next node, which is 7. When you call the heapify method on the node of 7, you are trying to restore the heap property of the subheap with its root as 7. Is this a max heap? No, 7 is a parent, its largest child is 10, and 7 is smaller than 10. So, the values of the 2 nodes need to be swapped. Like this. And now it becomes a max heap again, so we would move on. The next node to traverse is 3, which currently sits at the root level. When you call the heapify method on this node, you are actually trying to restore the heap property of the whole heap, with its root as 3. Like this. As a root node, 3 is apparently smaller than both of its children. So we need to swap it with its largest child, which is 10. Like this. After that, our focus is still on the node 3. It is still smaller than its largest child, which is 7. So we need to swap the 2, like this. Now, the node of 3 is at the leaf level, so we stop. Just to make sure we are on the same page. The heapify process on each of the subheaps that we just went over all happen in this original array. The tree structure here that you see is merely a visual representation. Now you know what this strategy is about. Let's talk about its worst case time complexity, so that we can compare it to the more naive strategy. To calculate the worst case time complexity, all we need to do is to add up the time it takes to heapify each subheap, expressed like this. There are roughly h minus 1 levels, where h represents the height of the heap. We want to heapify to any nodes at the leaf level, because we started with the last non-leaf node. That's how we get that h minus 1. At each level, there are a certain number of nodes. The heapify process on each of the nodes takes the same amount of time in the worst case scenario. To get the time it takes to heapify all the nodes at the same level, you need to multiply the node numbers with the time it takes to heapify a single subheap. There are some things that we need to clarify as we start doing the actual calculation based on this idea. First, in this strategy, we apply heapify process backward from the last non-leaf node to the root to make it more convenient for us to estimate the time complexity. We will deem the leaf level as level 0. As we move upward towards the root, we will increase the level number. So the second bottom level is level 1 in our eyes. So basically we treat the level numbers in the same way as a for loop. Second, the number of nodes at each level can be estimated as is shown here. We covered this in the past, in case if you remember. In short, if there are n nodes in a heap, to get the total number of nodes at the leaf level, you just need to divide n by 2 to get the number of nodes at the second bottom level, or say level 1. You can just keep dividing n by another 2, so that will be n divided by 4. To get the number of nodes at the third bottom level, or say level 3, you simply keep dividing n by another 2, so that's n divided by 8, and it goes on and on towards the root. The same pattern holds for every level. If you combine what we just mentioned, we will go from the bottom to the top and treat the leaf level as level 0. That will give us a way to estimate the number of nodes at each level using this formula. So that's n divided by 2 power to I plus 1, where n represents the total number of nodes in a heap, and I represents the level number. Now we know how to estimate the number of nodes at each level. We can actually quantify the time complexity Tn. Tn can be expressed like this. The number of nodes at level I is n divided by 2, then power to I plus 1. The work per node at level I is in proportion to I. In case if you are confused by this, remember that when we call heapify on each node at a level, we are actually trying to restore the heap property of a subheap, whose root is at this very level. The heapify method runs on a time complexity in proportion to the height of this subheap. If you focus your attention on the term inside this summation, you will see that n has nothing to do with the summation at all, and you can actually extract it out like this. Now, the summation term becomes something that you have seen in the past. The geometric series. As the upper cap of the summation grows towards infinitely large, it can be estimated to a constant number. As a result, Tn can be estimated to simply n multiplied by another constant number. In other words, the time complexity of this strategy is simply big O of n, which grows at a linear time. As you can see, the second strategy is definitely more efficient than the first one. Fixing a broken heap is certainly much faster than keeping calling the insert method to build a heap from scratch. When you are given a linear data structure to build a heap, you should always think about this strategy instead of the more naive one. That's everything about how you build a heap. Let's move to discuss how to use heaps for sorting purposes. The scenario that requires sorting using heap sort is no different from when we use other sorting algorithms such as a merge sort or quick sort. You are given a linear data structure with elements, and you are asked to sort the elements. How do you do it using the help from a heap? You will typically follow a set of steps. First, you will start by building a heap from the input array. After that, you will repeatedly extract the max or the min value by calling the delete method on the heap iteratively. If you build a max heap, the delete method will extract the max value. If you build a min heap, the delete method will extract the min value. When you place all the extracted values in a different array, they will either be in ascending order or descending order. For example, if you are given an array like what you see here on the screen, when you build a max heap out of it, you will end up with an array sorted in the descending order. To map these steps to pseudocode, you will have this. The heap sort function takes a single parameter a, where a represents an array. The heap sort function starts by preparing an empty array. After that, it calls build heap function on a, which will turn a into a heap. After that, it calls the delete method iteratively to store the returned elements in the prepared array. The delete method is the same method as we covered in the last video, so we won't get into its details here. Heap sort largely relies on the help from two helper methods that we developed in the past, including build heap and the delete methods. We know that the time complexity of the build heap method is big O of n in the worst case. What about the for loop that iteratively calls the delete method? If we want to measure the worst case time complexity of heap sort, we have to have a good sense of the time complexity of this for loop. We already know the worst case time complexity of the delete method as log n, when n is the heap size. When the delete method is called for the first time, the time complexity will be certainly big O of log n, as the heap size is still n now. After that, the heap size becomes one element smaller, which is n minus 1. So when the delete method is called again the next time, its time complexity becomes big O of n minus 1, as the heap is one element smaller now. When the delete method is called again for the third time, the time complexity becomes log n minus 2. This will go on and on until you run out of elements in A, and the time complexity is gradually reduced from log n to log 1, like this. To get the total time complexity of the for loop, all it takes is to add all these different time complexity up, like this. Based on the logarithmic property, you can combine all these individual terms, so it becomes big O of n factorial. The factorial of n is always smaller than n power 2n, and the log of n power 2n is equal to n multiplied by log n. As such, we can estimate the worst time complexity of the for loop to a term that's more familiar to us, which is n log n. So the total time complexity of heap sort will be equal to big O of n log n plus n. N log n is the dominant term with a higher growth rate. As such, you can ignore n, which grows more slowly. That said, the time complexity of heap sort can be estimated as big O of n log n. In this video, we learned about heap sort, particularly how to build a heap efficiently and how to use a heap for sorting purposes. That's everything about this video. Hope you learned something new.